Okay, nice to see you all again. As you can see, I'm recovered from the 24-hour flu. I don't recommend it, but anyways, it's in the past. Okay, back to evolutionary robotics. Hopefully you were all able to watch last year's recording of evolutionary algorithms. There were several important concepts that were introduced in Lecture 5 about evolutionary algorithms. Two I want to just highlight and make sure that they're consolidated for you. Number one is that evolutionary algorithms is an umbrella term. There are lots of different evolutionary algorithms, and in Lecture 5 last year, I went over several of them. There's hundreds, if not thousands, of different flavors. We're going to be using one particular evolutionary algorithm called the genetic algorithm. We'll be using that later in assignment 8 or 9, I don't remember. Second important concept was the concept of the fitness landscape. This is going to come up again and again in this class. So if that concept is still a little vague in your mind, while you have some breathing room now at the beginning of the semester, I recommend you go back and watch those sections of Lecture 5 that talk about what makes up a fitness landscape. It's going to be a very important intuition pump or thought tool for us for the rest of the course. Okay. All right, that's lecture material. Today we're going to cover physical simulation, and that will conclude our discussion of the three main tools of the trade, the three main parts of your system that you're going to be building over the next few weeks: artificial neural networks, evolutionary algorithms, which are going to act inside of a physical simulator that you're already building. We may or may not finish all of Lecture 6 today. We might start in on the first few slides of Lecture 7. We'll see how things go. Okay. Orientation about assignments. Undergraduates, you're working on assignment 3. Graduates, you're working on assignments 5 and 6. And just as a reminder, in assignment 1, you covered links. In assignment 2, you covered joints, both of which we're going to talk about today in our discussion about physical simulation. In assignments 3 and 4, you're going to be covering sensors and motors, and then the brain of the robot in assignments 5 and 6, the neurons and synapses that make up the brain or the neural network controller of your robot. Okay. Assignment 1, 2, 3, 4, 5, 6. So before we dive into physical simulation, let's talk about the physical simulator that you're using, which is PyBullet. And PyBullet provides for you these two building blocks, links and joints. PyBullet itself is not a robot simulator. We need these other things in order to make even a simple Bratenberg vehicle. So PyroSim is a wrapper that I wrote to try and simplify you adding these additional robot parts on top of PyBullet. So very cleverly named, PyroSim is a robot simulator for PyroSim. It sits on top. So we're going to talk about links and joints in a moment, and then we're going to talk about how you can exploit the underlying physics to simulate sensors and motors, and then you are going to be responsible in 5 and 6 for adding neurons and synapses to your simulator. So we're going to start today in the basement or the engine room of your code base, which is the PyBullet physical simulator. Okay. All right, off we go. Okay, again, a little bit of history here. So in the 1970s and the early 1980s, as these things called computers started to move out of universities and big corporations into people's homes and offices, people figured out that you could use these new things called personal computers to do cool things like make awesome graphics. And the way this was done at the beginning was, as an artist, you came up with the scene, the idea, the two-dimensional world or the three-dimensional world you wanted your computer to visualize for you. As the artist, you would define the position, Where in three-dimensional space, we'll do this in 3D, where in three-dimensional space does each object sit? What is the three-dimensional orientation of that object? You had to describe that to the computer, and you obviously had to describe the three-dimensional shape of the object at a given point in time. And then if there was more than one object in the scene you were trying to construct, you had to come up with the position, orientation, and shape for all of those as well. You'd give all that information to your personal computer, and after a few minutes, it would render one frame of what that scene would look like. You would describe the new position, orientation, and shape of each object at the next time step, and it would render the next frame, and the next frame, and the next frame, and the next frame. And if you had a high-powered enough personal computer in the early 1990s, 1980s, you could then also tell it to stitch all those frames together and make a movie. It was magic at the time. Yeah. You can tell from the way I'm describing this, it was very labor intensive. It partly automated the creation of visual scenes, but the author or the artist still had to do a lot of the heavy lifting. In this description of computer graphics, we've already introduced an important concept in computer graphics and in physics engines, which is the concept of a time step. So you can see we've got time step t, we've got time t, t+1. The assumption, even way back before physics engines existed, is that there was some interval of time between t and t+1. That was up to you to decide on. If in this movie you were trying to construct, there was a low frame rate, then there would be a lot of movement from one frame to the next. If the amount of time between two instances of time was much shorter or much narrower, then you, as the author, would update the position and orientation by a smaller amount. Okay, choosing a good time step, not so important in computer graphics, but when we get to physics engines, choosing a good time step is very important and is not necessarily an easy thing to do, and we'll come back to that idea later. Okay, so we've got this concept of time steps. In 1999 and into 2000, there was a company in the UK that started to create something that became known as a physical simulation. They created arguably the first one. It was called Math Engine at the time. It was a physics engine that did a lot of the math on behalf of the artist. The computer took over computing the new position and orientation of objects in your scene. So with the arrival of Math Engine in 2000, the artist could now, like before, start by defining the initial position and the initial orientation in three-dimensional space and the shape of their objects, but they would then assign some additional physical parameters to each object in the scene, like the mass of the object, its friction properties. Is this object covered in sandpaper or is it smooth? What happens when this object comes into contact with other objects? You would define some additional information. You do some additional work up front, but you would recoup that manual effort once you turned on the physics engine and things started rolling. One other detail you had to define is the computer, the physics engine is going to start updating the positions and orientations of the objects in your scene. What should the computer do if any two objects come into contact with one another? Should those objects pass through one another? Should they collide and deform and then bounce back? Should they act like two steel ball bearings that the moment they come into contact, they immediately start moving in opposite directions? How should the computer handle collisions when they occur? So there's a lot of work you have to do up front, and you're still doing a lot of work up front, but PyroSim hides some of that from you. Once you've done all that, then you would start the physical simulation, and the physical simulation would step from one time step to the next, and you could just sit back and watch your animation or your simulation play out in front of you. Yeah? Okay. So how does a physical simulator discover the new positions and orientations of your objects. It gets complicated very quickly, but the basic way it does it is to use an equation which hopefully is familiar to you from high school physics. F equals ma. Force equals mass times acceleration. If you rearrange this equation into A equals F divided by m, you'll notice that you've already given the physical simulator mass. It knows the mass of an object, like, for example, this circle that we've placed a certain distance above the ground. The physical simulator can figure out on its own the forces that are acting on that object. In this very, very simple scene here, I've placed an object above the ground, and in this simple simulation, there's one and only one force acting on this object. What is it? Again, high school physics. Gravity, right? Which is, I'm Canadian, I want it in units. I want it in metric, sorry.
9.8 meters per second.
Thank you very much. 9.8 meters per second in a negative direction, right? It's pulling down. So we have the mass. So the physics engine has the mass of this object. It has the force of this object, so it can calculate the acceleration of this object. It knows the position of this object at time t. It now knows the acceleration, and it can combine those two pieces of information to find the new position of the object at the next time step. And the physics engine renders the frame at time t, then it renders the frame at time t plus 1, rinse and repeat. This introduces the second important component of a physics engine, this concept of time step, and also this concept of a loop. So whenever a physical simulation is running, there's usually a big while loop or a big for loop, and every pass through that loop is one time step. When the physics engine gets to the end of that loop and goes back to the beginning and starts again, an amount of time passes, which is the time step, which you usually set. So far, so good? Okay. What happens when this object gets to this position at time t plus 1? What does the physics engine have to do now? Things get a little more complicated. Let's assume that you've told the physics engine that this object, the ground, and this object, the ball, should not interpenetrate one another, should not pass through one another. I'm sorry, I realize I misspoke. Step number 2 here is how objects are attached together with joints. We'll get to joints in a moment. In my little cartoon example here, there aren't any joints. There's just one link, and the position of that link is changing. One other piece of information you need to define is which objects can pass through one another and which cannot. So let's assume at the second step here, you've told the physics engine, don't let this object or this object pass through one another. How does the physics engine deal with that at this point in time?
The ground applies an upward force.
The ground applies an upward force. So at time step t plus n, the physics engine realizes that these objects are in contact with one another. That's called contact detection, and we'll talk about that in a few minutes. So it's detected that these objects are in contact with one another. It goes and looks at another part of the code where we told it they should not interpenetrate. So the physics engine has to incorporate that additional piece of information that is now relevant at this point in time to compute the new position of this object at time t plus n plus 1. So at this point in time, the physics engine says, well, the mass of this object is still the same. Gravity is still pulling at minus 9.8 meters per second, but these objects should not interpenetrate. So I'm going to tack a second force onto this object at this moment in time, which is a force that's counteracting this collision. Can you be more specific? What's the magnitude and the direction of this force?
It's 9.8 meters per second squared up.
9.8 meters per second squared up, right? Which cancel each other out. Those two forces cancel each other out, and we have 0 divided by whatever the mass of this object is. So the acceleration of this object at this point in time is 0. Technically, it should probably be a deceleration, but in this cartoon example, I just want you to get the intuition here. So very quickly or instantaneously, the position of this object stops, and when you watch the resulting movie, I'm not sure why the screen is flickering off and on today. There we go. Okay. It very quickly comes to a stop, and the position doesn't update anymore. Yeah? Okay, so that's how physical simulation arose from this earlier technology of computer graphics. Any questions? So far, so good? Okay. In most of the slides in today's slide deck, we're going to actually look at some code snippets. You do not need to be able to read these code snippets. They're there mostly as a reminder of the underlying code. We're going to build up our intuition today of physical simulation, which is instantiated in code. In your case, it's PyBullet. If you had taken this course 7 years ago, you would have been doing this in ODE, a different physics engine, which stands for Open Dynamics Engine. Different physics engines have pros and cons. When we start looking at soft robots, robots that are made of silicone or rubber or jello or biological cells, soft robots, we're going to have to switch from another physics engine because PyBullet only does rigid bodies. Soft body simulators are much more complicated, and we'll talk about them when we get to soft robotics. Okay, so a few years ago, students who took this class did everything using Open Dynamics Engine, which wasn't in, it's not in Python. It's in another history lesson for today.
C.
This is C. Okay, if you don't know C, that's okay. It's a good exercise to try and read code from a language you don't know. It's kind of like, as an English speaker, if you try and read Dutch, you almost can because they're very, very similar. Not quite. Okay. All right. So we're going to use some snippets from ODE today to illustrate these intuitions. All right. Preliminaries. As I mentioned, in any physical simulation, you as the author, the artist, or the roboticist have to do some work up front, and then you get to recoup all that effort. So in ODE, you had to call some preliminaries and provide a few constants, which we won't talk about today. You would then create a world. This is this three-dimensional space that your robot is going to exist inside. You would then create what's called a contact space. We'll see contact spaces again in a few minutes. A contact space contains all the objects that cannot interpenetrate. Okay, it's kind of a non-intuitive thing to think about. In a moment, or I guess you've all gotten through assignment 2, so you know the basic idea of a joint. A joint connects two links together. So imagine my upper arm is link number 1, my lower arm is link number 1, my upper arm is link number 2, and my elbow is the joint connecting them together. In PyBullet, you might place the upper and lower arm touching one another or even maybe overlapping a little bit, which means by definition they're already interpenetrating. And PyBullet, like the ball in the floor, might try and push these objects apart. So you need to tell the physics engine, do allow these objects to interpenetrate. They're supposed to be touching one another, and they're allowed to also push within one another to a small amount. Don't try and pull them apart. Yeah. So there is a subset of objects in your simulation that should not interpenetrate, and some that should. So even in the case of a 2-link, 1-joint robot, these two objects are allowed to interpenetrate, but if these two objects fall and hit the ground, this object should not interpenetrate the ground, and this object should not interpenetrate the ground either. So there are spaces or subsets of objects that should not interpenetrate. It's a little complicated, and again, most of those details are being hidden from you, but today we're kind of pulling back the hood and looking at what's going on underneath. It seems like a complicated way to do things. There's a reason why, and we'll get to that reason in a moment. You then, in ODE, you would create a bucket, and at the beginning of the simulation, this bucket is empty, but this bucket from time to time fills up with pairs of objects temporarily. Then those objects are pulled back out of the bucket. What are the pairs of objects that go into this bucket? Pairs of objects that are detected to be in collision. So in our cartoon example back here, this contact group was empty at time t, empty at t plus 1, empty at t plus 2, but at time step t plus 1, there was one link pair inside this group, and it's the objects that are in contact. Every time step of the simulation, the simulator would look inside that bucket, and if there were object pairs that were in contact with one another, the physics engine would add a force pushing them apart. Okay. You are then free to set various aspects of your world. When I asked for gravity, you all said minus 9.8 meters per second, because of course that's acceleration due to gravity, at least on this planet. You can set gravity to different constants if you're simulating robot rovers that are going to visit other bodies in our solar system. Okay. There are other hyperparameters or settings for a physics engine. Again, most of these are hidden. Some of them have to do with friction. Some of them have to do with the distribution of masses of inside an object, kind of details that we're not going to worry about for now. If you're interested in physics engines and specifically how physics engines differ, you've got some experience now with PyBullet. If you want to go see some of the differences, here's a link that points to ODE and the specific lines that we're talking about today. So far, so good? Okay. All right. More preliminaries, things that you have to do up front. You've already done this in assignment 1. You've defined various links, which are known as bodies in ODE. They're known as objects in other physics engines. It's confusing. They have different names. They're the physical Lego bricks that make up your robot, the physical parts of the robot. So in ODE, here's somebody in their code on line 4 creating a body, and they're putting that body into the world that they just made. You can make multiple worlds and put different bodies into different worlds in one simulation. Usually it's one world, multiple bodies. In ODE, you would then define another data structure that describes the mass of an object. Here you can see that this person is setting the mass for a box, and there are 4 numbers here. The first number is the density of the object. These 3 other numbers are not the length, width, and height of the box. They're the distribution of mass, kilograms, Canadian, the metric system. Doesn't really matter. In this case, they are defining how the mass is distributed inside a box. Imagine you have a cardboard box and you fill it to the brim with textbooks. It's completely filled. You have a uniform mass distribution inside. Imagine another cardboard box with exactly the same length, width, and height, but you put one textbook in the back corner of that box. When you go to lift it up, the mass distribution inside the box is uneven. You can define that in the physics engine. For now, again, we're hiding that detail from you. Every object, every link you create in PyBullet has a certain weight or mass. That mass is distributed evenly inside that link. Okay. ODE was good for some things. It was bad at other things. Like, for example, it had some redundancy. So we've just kind of defined the density. Then we defined the overall mass here. Not important for our purposes. What's important is to just see we're setting the mass of the object, and we can distribute the mass if we want. We have this object called a body. We have an object here called body, and we are setting the mass. We're assigning this thing to this thing. We've defined this data structure that describes the mass of the object, and then we attach it to the object. And we then set some other parameters of this body. We've just set its mass properties. We now set its positional properties, where it starts its life in the simulation, in three-dimensional space. So it's starting at y units, which of course meters, 6 meters above the ground. So far, so good? Okay. What are we missing? What are some important physical properties of this object that we haven't defined yet, that the physics engine is going to need? The size. We haven't set the length, width, and height yet. In ODE, you didn't set the size here. You set it somewhere else, and we'll get to that in a moment. It's a little confusing. We're setting the physical properties of this object, but not its geometric properties yet, not its size or shape. We've just set the position of the object in three-dimensional space. We also have to tell the physics engine what that object's orientation is in three-dimensional space. If our object is a sphere, then of course it doesn't really matter what its orientation is in three-dimensional space because the sphere is symmetric in all possible ways. But if I want to create an object that looks like this, I can place it at this position like this, or I could put it at the same position like this, like this, like this. So I need 3 more numbers. Actually, I need 4 more numbers to specify where this object sits in three-dimensional space. And it seems like an easy thing to do, but it can get a little confusing pretty quickly. So again, we've hidden this detail from you. When you create a link when you created links in assignment 1, you did not set the orientation of that object. If you do want to play with the initial orientation of objects, you can skip ahead to module P in the subreddit. There's a bunch of tips and tricks there. And on steps 26, 27, and 28, it'll tell you how to go into PyroSim and uncomment or reveal that piece. And now back in your own code, you can now set the initial position and three-dimensional orientation of the object. So you'll see as you continue on in the course, we've hidden a lot of stuff from you, but as we go, we'll give you pointers about how you can go in and reveal things if you want. For now, it's completely optional. You don't need to. Okay, why do we need 4 numbers? There are different ways to specify an object in three-dimensional space. The most common one and the most difficult one to wrap your mind around is quaternions. There's different ways to define quaternions. There's one way to define it using imaginary numbers. We're going to try and avoid imaginary numbers. For those that are interested in it, you can go and do it. We're going to try and do this with sticking just to the reals today. Okay, here we go. We want to place this object, this marker, we want to set its orientation. So we can take 3 numbers, which we'll call x, y, and z, which define a three-dimensional vector a vector in three-dimensional space. And we're telling the physics engine to use x, y, and z to align the long axis of the object along x, y, and z. So we will eventually tell the physics engine what the length, width, and height of an object is. We haven't done that yet. So it has that. It has L, W, and H. It finds the biggest of those 3 numbers, what's the longest axis of this thing, and it takes that long axis and lies it along this vector. And then the 4th number, theta, says now roll that object by a certain amount around that long axis, and that will uniquely specify an orientation for this object in three-dimensional space. Make sense? If you're dealing with a rectangular solid, you need all 4 numbers. I could take my smartphone and align it along this vector, but it could have all of these different rotations. That's why I need the 4th number, theta, to say what angle around that vector does my object sit. If instead the object that I'm specifying in three-dimensional space is a cylinder is symmetric around its long axis. So I can get away, I don't need that 4th number theta. I can just define the vector that that cylinder is going to lie along. And again, going back to a sphere, I don't need to give it any of these 4 numbers. I just need to tell it where it sits in 3-dimensional space. Sound good? Okay. Question?
What if you want it perpendicular to the vector?
Then define a vector that's perpendicular to the vector you have in mind. We're setting the initial orientation of the object.
Is the vector defined from the origin then?
Is it defined from the origin? No. Sorry, good point. This 3-dimensional vector passes through the position you want to start the object at. Sorry, I missed that detail. Yes, good point. So I know this is the position at which I want to place my object, and I want it to sit upright. So I define a vertical vector. No, I want it to start here, but I want it to point towards the door of the room. So define a vector that points in that direction, and so on. Yeah? Okay. A question that may be occurring to you is this seems overly complicated. Yeah? Okay. There's a simpler way, which is to use just 3 numbers known as yaw, pitch, and roll. I always get these confused. So, okay, I'm an airplane. I'm pointing in this direction. This is roll. Makes sense? This is roll. Pitch is the nose of the plane goes up, the nose of the plane goes down, and yaw is the plane starts to do this, right? None of which you want an airplane to do when you're on it. You want it to change positions, but not yaw, pitch, and roll. Yeah? That seems so much simpler than quaternions. It turns out that simplicity of yaw, pitch, and roll makes things complicated for the physics engine. There's problems with defining orientation with yaw, pitch, and roll. Quaternions are more complicated, but they're smoother and easier for a physics engine to use. We're not going to go into the reasons why. If you want, go and Google quaternions versus yaw, pitch, and roll. You'll find the reason why. Okay, one other observation I want to make at this point is when we're dealing with objects in 3-dimensional space, we're usually dealing with 6 numbers: x, y, and z, location in space, and yaw, pitch, and roll, how something is oriented x relative to x, y, and z. So 6 numbers are usually enough to uniquely specify an object. It's enough to specify an object that is at rest. But if an object is moving, we're going to need more than 6 numbers, and we'll get to that shortly. So far, so good?
I've seen a lot of old systems, at least before GPS. They would just have an accelerometer, and then you take the derivatives over to find your position and velocity.
If you have access to how something is moving, you can work backwards to things like velocity and position and orientation. Yes, that's right. For our purposes, remember, we haven't even turned our physics engine on yet. We're just telling it the initial state of the robot in its world at t0, at the beginning of time. Other questions? Okay. All right. We'll come back to specifying the geometry of links in a moment. We're kind of doing things in a weird order today. Joints you've already come into contact with, no pun intended. Joints connect links together, but more technically or more truthfully, what they actually do is remove degrees of freedom. As roboticists, we're going to use this term a lot in this course. What is a degree of freedom? It turns out that for links, for individual objects in your scene, there are 6 degrees of freedom. There are 6 ways in which the object can move. We've got an object sitting somewhere in 3-dimensional space. We have its 3-dimensional orientation. Let's think about the dimensions along which it can change. It's got an initial position, so it can move along the x-axis. It can move along the y-axis, or it can move along the z-axis. So there's 3 degrees of freedom, which allow the object to move like this, but you'll notice that I'm not changing the orientation of my marker. we can then think about the object changing its yaw, pitch, and roll. It can rotate about the x-axis. It can rotate about the y-axis, and it can rotate about the z-axis. So it can change its x, y, and z, and it can change its yaw, pitch, and roll, which gives us the 6 degrees of freedom. If you define two separate links in your simulation, you've got 12 degrees of freedom. Each of the two objects can move along at 6 degrees of freedom. The moment we connect two links together with a joint, that joint is going to remove one or more of the degrees of freedom of the links that are attached together. These two links are no longer free to move along any of its 6 degrees of freedom. Okay, let's see how. Let's have a look at my elbow joint. Luckily, my elbow joint constrains my lower arm from moving away from my upper arm. That's kind of the whole point of the elbow joint. Yeah? Okay. So let's assume that this is the Z. Let's see, did I get that right? Yeah, this is the, oh no, sorry. We'll do X along here. Let's just think about the X position of my lower arm and my upper arm. If this tries to move this way, so does this one. They cannot independently change their X coordinate, luckily for me. I'd be in a lot of trouble if that weren't the case. So the elbow joint has removed at least 1 degree of freedom. Has it removed any others? If this is Z, can this one and this one change their Z coordinates independently? Again, luckily not, right? So now we're down to 4 degrees of freedom for both of them. We've removed, the elbow joint has removed 2 degrees of freedom from this one, or independent degrees of freedom from this one, and removed 2 independent degrees of freedom from this one. Are we done? What about this one? Can I move my upper arm this way and this one this way? Luckily, again, not. Okay, we're down to 3. Let's do yaw, pitch, and roll. What's possible here? Can I rotate this one this way? And can I rotate this one this way? I'm obviously drawing it in the air because I can't. So there goes one of the 3 rotational degrees of freedom. We're down to 2. What's left? Let's think about the vertical axis. So yawing this way. Can this do this and this do this? It's a bit of a physics lesson and an anatomy lesson today, right? Again, I'm drawing into the air because I can't. One left. This one. Can I rotate my upper arm this way and my lower arm this way? Kind of. They can both change this. What is this one now? Yaw, pitch, or roll. We'll call this one roll. Doesn't really matter. There's one of them that's still kind of independent. Not quite, because I can't do this one this way and this one this way. I guess I can if I do this. So we're really down. Their elbow joint has taken away 5 degrees of freedom from the 2 objects and left just 1. Okay. We won't go through all 12. What about your knee joint? Think about your upper leg and your lower leg. What's possible? I hope none of you have ever blown out your knee, but if you do, it's because you violated one of the constraints that your knee was trying to apply, which is to, again, remove everything except one rotational degree of freedom, right? I'm not going to show you in this class my upper leg doing this and my lower leg doing this, right? If we were, you'd be walking me across the quad to the ER. Not a good thing, yeah? Okay, so in this class, we're going to mostly be dealing with hinge joints, which are hinges. They remove all but one rotational, they remove all the positional degrees of freedom and 2 of the 3 rotational degrees of freedom. I see some of you doing your morning calisthenics. That's good. There are different kinds of joints in a physics engine, and there's different kinds of joints in you. Your elbow and your knees are the easiest one. What about your shoulder? What does that make possible? Now you got to think about the degrees of freedom of your upper arm relative to your torso. How does your shoulder constrain the relative motions and the relative orientations of your arm relative to your torso? Does it do the same thing as your elbow joint and your knee joint? Does it remove all 3 positional degrees of freedom and 2 of the 3 rotational degrees?
It removes your positional freedom, but you can still yaw, pitch, and roll.
You can use, it removes positional independence. Again, a good thing. You don't want your arm to wander away from your body, right? It keeps it connected to your body. If my torso goes this way, so does my arm, and so on. But you have most of the remaining 3 rotational degrees of freedom. There's 1. My arm is yawing while my torso is not. Here's my arm pitching while my torso is not. So they're independent. I could do the same with my torso and try and keep my arm still, but I'm going to hurt myself. And then the last one, kind of. You can go a little while and it gets pretty constrained pretty quickly. So there's really, technically, according to your shoulder, there's about it leaves 2.5 degrees of freedom, 2.5 rotational degrees of freedom, relative rotational degrees of freedom left. It's probably not exactly 0.5, but I'm not a physiologist. The point I want you to take away is joints in a physics engine and joints in you remove some of the positional and rotational independence of objects or links. Okay. All right. So back into some code. Again, ODE, it's in C. I don't expect you to be able to read this perfectly. But from the words, you can see that we're creating a particular type of joint called a hinge. And we're adding that joint to the world. The most important thing we have to do is tell the physics engine that this new joint, which we're calling hinge, connects 2 bodies together. In PyBullet, it connects 2 links together, which immediately tells the physics engine that when it tries to compute the new positions, compute the new positions and the new orientations of objects, it's going to have to take into account the joint. How do you think a physics engine uses a joint to constrain the new or alter the new position and the new orientation of objects as the physics engine starts running? Remember our example of the falling ball, and then suddenly it stopped falling when it came into contact with the ground. How did the physics engine make that happen?
It applies opposite forces whenever an object violates its constrained degrees of freedom.
Absolutely. The moment that 2 links are moving around and the physics engine is trying to compute the new position and the new orientation, there's a force that's applied that might counteract that new position. It's a new force that gets added and gets incorporated into this calculation, which is conducted, this calculation is conducted for every link in your simulation at every time step. When you try and rotate your arm too far this way, there are very real physical forces that are being applied to your arm and your shoulder and this part of your torso by the tendons in your body to stop this relative change in orientation. Same thing in a physics engine. Where did we get to? There we are. Okay. The other thing seems a little bit odd is we need to tell the physics engine where the hinge's position is. It seems kind of obvious, right? Where's the position of my elbow? Well, it's right here where these two objects come into contact with one another. This object and this object. Where's my knee? It's exactly where this object and this object come into contact with one another. Why are we even telling the physics engine that? It should be able to figure out on its own where the position of that joint is. Most of the time in a physics engine, it makes sense to put a joint exactly where the two objects come into contact. But there are a few exceptions to that rule, and that's why the physics engine forces you to do it. For our purposes, not important for today. Throughout this course, when we talk about joints, we might talk about the joint's position, we might talk about its anchor, we might talk about its fulcrum. They all, for our purposes, those things all mean exactly the same thing. Okay. The last thing we need to define is the axis of the hinge, which is a little confusing, so we're going to take some time to talk about it. In PyBullet, it's not known as the axis, it's known as the joint normal. And defining the joint normal, again, we've hidden it from you because it's kind of non-intuitive. When you get to your final project and you're going to want to make cool and complicated robots, you're going to probably need to set the axis or the normal for your joints. And so there are instructions how to do that in the quadruped module N, which is assignment 9 for our purposes. So when you get to assignment 9 and you get to steps 23 through 36, you're going to be revealing that piece which is currently hidden in PyroSim. Okay. What is a joint axis or a joint normal? Again, I'll use those terms synonymously in this course. They tell us how they give us more information about how the joint removes positional or rotational degrees of freedom from an object. Okay, hard to draw in 3D, so I will try and act this out again with my upper and lower arm. Let's assume that we have one link here and one link here. So here's my upper arm, and here's my lower arm. And we're going to assume that you've placed all these positions so that the position of, or the anchor of the joint is sitting at x equals 0, y equals 0, z equals 0. Okay. Now, we're going to assume that to begin with, we want these two objects to be able to do this relative to one another, but not, that's the only relative degree of freedom we want this system to have. Okay, how do we tell it that this can happen, but not this? Yeah, we want to take away this one, this one. We just want to leave this one. We define the axis using a three-dimensional vector. You can think of the axis or the normal as a vector that is leaving the position of the joint. So our joint is at 0, 0, 0 to make things easier. In this case, I am setting this to 0, this to 1, and this to 0, which is defining an imaginary vector pointing vertically out of my elbow joint. It's sometimes called the joint normal because, again, if you remember from your algebra class, there is a two-dimensional plane, a unique two-dimensional plane normal to this vector. If you define a three-dimensional vector, whether you realize it or not, you are also implicitly defining a unique two-dimensional plane that is normal to it. Yeah. So if I define if I set the axis to a vertical vector, then I am implicitly defining the xz plane, right? The horizontal plane that's normal to it. And this is my way of telling the physics engine, I want these two objects to rotate relative to one another through the horizontal plane. Everybody see that? Okay, that's what's true at t equals 0, the beginning. But of course, there are two links here that are being acted on by gravity. Maybe I shoot a bullet at one and it hits one, and then now this one suddenly has some additional forces that are being applied to it, and I can't do this with my upper and lower arm, but these two links start changing position and orientation in three-dimensional space. This plane that they rotate relative to one another stays relative to these two objects. When I define this horizontal plane, I don't mean that these two objects always keep rotating through the horizontal plane. That two-dimensional plane, which was originally horizontal, travels with the two objects. Yeah? So this is true. From my perspective, my upper and lower arm are still rotating through a horizontal plane, horizontal relative to me. Make sense? Okay. All right, let's imagine instead we had exactly the same initial positions of our two links. We had our joint at 0, 0, 0, but now I want these objects to rotate relative to one another like this. What's the joint normal that I need according to this coordinate scheme? It's not the vertical axis anymore. I want these two objects to rotate like this. How do I tell the physics engine that that's what I want? Exactly, right? So when I'm doing this, I'm showing you that I want these two objects to rotate through the x, y plane. And so I define 0, 0, 1, the vector that lies along the z-axis. And that implicitly tells the physics engine the xy plane, please. Yeah?
For these, you're using unit vectors, but also just because it's simpler. Does Parasim or Pebblets allow you to use non-unit vectors?
Yes, you can use non-unit vectors. It doesn't matter. In this case, you might have noticed the magnitude of this vector doesn't matter. It's just the orientation that matters. Yeah? Okay, again, this seems like a complicated detail. Why does this matter? Well, in the first few assignments, you're creating a relatively simple robot. But in your final project, like many roboticists that have come before you, maybe you want to make an insect-type robot that looks something like this. Okay, hopefully you can visualize this six-legged robot walking towards you out of the board here. There are 1, 2, 3, 4, 5. Sorry, let me start again. That wasn't right. There's one joint here, one joint here, one joint here, one joint here, for a total of 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 joints. Did I get that right? There's a whole bunch of joints. We're not going to define the normals for all of them. I want you to think about this particular leg here. So this is the front right leg of our insectopoid here. I want you to think about the shoulder joint and the elbow joint. I don't know if there's any aspiring entomologists here, lovers of insects. All insects have 6 legs, I think, without exception. And they all have a particular way that they move their legs. What is it? If you've never thought about such things before, you're going to start spending a lot of time doing so in this course. You've all seen insects move around, you must know. Given what we've talked about before, so far, hopefully you could describe it mathematically, but in the interest of time, show me. Good start, okay, kind of. Is the insect's shoulder joint like our shoulder joint? Is it free to do this? What about I'm calling it an elbow joint, but let's put these in scare quotes. Elbow joint, shoulder joint.
I would say that they, like, their shoulder, it hinges up, their elbow goes forward.
Okay, shoulder hinges up. So I heard this. This is what you mean by up, right?
Yeah.
Okay, let's just stick with that for a moment. Yes, if you've ever seen an insect, among other things, this is one thing it can do with its front right leg. What's the normal? What's the joint normal? If you wanted to tell the physics engine that the insect robot should be able to do this, I don't do enough yoga. If I did more, I could go further. Yeah? Okay. Do some of this. What's the joint normal? Let's use this coordinate system. The insect is facing you along the z-axis. The z-axis is from me to you. It's still along the z-axis, right? We're asking it to do x and y. What else can an insect leg do? Is this the only thing the shoulder joint can do? If it was, and you're an insect, you're kind of in some serious trouble, right?
Rotate around the x-axis?
Rotate about the x-axis, which is, have I got this right? This way. Okay, so you've got the normal right and the motion right. Is that what the shoulder joint does? Not quite. It's close. It's like us. It can do this, which is, so we've got this motion and this motion. It's got to be the y-axis, right? It rotates about the vertical axis. It's able to swing this piece and this piece forward and backwards. So we've got this. What does this do? Technically, you could walk, even if this was a joint that removed all degrees of freedom. You just weld it shut.
Would that then be the x-axis? The elbow joint being the x?
I'll just keep my upper arm still for a moment. What should this one be doing? How should this one rotate relative to this one? Intuitively, you can feel it. If you're doing this, and you want to take a big stride, insects, for various reasons like us, often want to move really fast. If you've got this, imagine this is frozen solid for a moment. You get to release part of it. You can give one of the 6 degrees of freedom back to the insect. Which one is it?
Rotation about the z-axis.
About the z-axis, which is this way, pointing towards you, which defines rotation through this plane, which is absolutely what you want, right? If you can do this, that's good, but if you can also do this, that's much better, yeah? Okay, so we just intuitively thought this through, and we might have got some of the details wrong. You can go research insect physiology, but you would then tell the physics engine using some code where all the joints are, what the normals are, and then once you start this thing moving around, it's going to start to move in a way that looks like the movement of an insect. The movement might not be coordinated because we haven't set the parameters for its neurons and synapses yet, but we've got the physiology more or less correct. Yeah? Okay. Okay. Now we're going to come back to links, and we're going to talk about the geometry. In most physics engines, there's a separation between physical aspects of an object, or its inertial properties, which have to do with its mass, and its geometric properties, which seem kind of silly, but there's reasons why physics engines do this. So let's go back to our earlier code where we were creating a single object back here, and we called it a box. So we were distributing some mass uniformly along a length, along a width, and along a height, but we had not specified what that length, width, or height is yet. We can do that. We do that here in ODE. So we've created a data structure called geom, which describes all the geometry of an object. And we then assign that in ODE. You would assign that geometry to a body. Think of this like wrapping a skin around an object that has some mass properties and positional properties already. Again, kind of a non-intuitive way to do things. Part of the reason why physics engines separates physical or inertial description from geometric description of objects is that one of the main things and the most computationally intensive part of a physics engine is dealing with collisions, determining whether objects have come into contact with one another and what to do with those objects when they come into contact. So anything we can do to make that computation simpler is going to get you back, is going to keep the fan from turning on your laptop. So one way to do that is to separate is to get rid of all the inertial stuff and just the geometry. We just need the skin of the object to do collision detection. Are any pair of objects in contact with one another? Seems like a simple thing to do. Why is this so computationally intensive? That's what we're going to see in a moment. I mentioned contact spaces before. Just bear with me. In this cartoon example here, we're going to assume that we're creating a simulation that's made up of 1, 2, 3, 4, 5, 6, 7, 8, 9 ball bearings. Not a robot simulation. We're just going to simulate a bunch of metallic spheres bouncing around together. We're going to assume that we've placed 4 of these ball bearings in one contact space and 5 of these ball bearings in a second contact space. And what a space does, any objects that are inside a space, at every time step, the physics engine, if I get my screen back, at every time step within a contact space, the physics engine is going to look whether any pair of objects in that space are in contact with one another. How many pairwise comparisons does the physics engine need to do in this cartoon example? In space 1.
4 choose 2.
Sorry?
4 choose
4 choose 2. Okay. An intuitive way to think about this is this object in contact with this object? Is this object in contact with this object? Is this object in contact with this object? No, no, no. Okay, next. Second object. Is this object in contact with this object? No, no, no. Third object. No, no, no. Fourth object. No, no, no. How many questions did we just ask?
That was 16. Or
Close, not quite. We visited 4 objects, and for each of those 4 objects, we asked how many questions?
3, 4.
We just conducted 12 collision. We just looked to see whether there were 12 collisions.
can't you reduce it by 1 each time?
Thank you. Okay, so this was horrible, right? If you're a computer scientist, you should be wincing now. We just expended a fair bit of electricity and carbon that we didn't need to. We could have actually come to the same overall conclusion that none of the 4 objects are in contact with one another using less than 12. How many fewer? Watch again. No, 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 no. I've already done something wrong. Which of those comparisons did I not have to do? Here's object 1. Is it in contact with object 2, 3, or 4? Go to object 2. Is it in contact with object 1, 3, or 4?
You can do it in 6,
Why 6?
because the first time you check 3, but you've already, when you move to the next one, you've already checked if that's made contact with the one you start with, so you can cut that one out, so you're only checking 2. And then when you do the next one, you that one's already been checked with the one before it and the one before that, so you only need to do one more check to the last remaining sphere.
That's exactly right. So to compress that into one description, if you think about it, if you already asked whether I is in collision with J, object I is in collision with object J, you don't need to check whether object J is also in collision with object I, right? Those two things either both have to be true or both have to be false. So we can do half as many, this many, yeah? Okay, how many over here using this? How many possible collision detection events do I need to test? 10? How'd you get 10?
5 times 4 divided by 2.
Okay. So over here, we've got 5 objects, and for each of them, and we do a comparison against all 4, but we don't do J compared to I if we've already done I compared to J, so we divide by 2. Here's a specific example with 4 objects, 5 objects. What if we have n objects in a space? What's the equation here that we use to know how many collision detection events?
Would it be n squared minus n divided by 2?
Which you probably got from,
Yeah, just distributed it out.
thank you. Okay. Everybody see the intuition for this compared to this? Okay. This is why your fan will often turn on when you're running a physics engine. We've got, let's go look down here. This is actually arguably a simpler situation. We still have our 9 ball bearings bouncing around, but they're all inside the same one collision space. How many collision detection events does your physics engine have to detect at every time step? So what is it? 9 times 8 is 72, divided by 2 is 36, right? So these are exactly the same scenes, but in this case, this is more expensive because we need to do 36 collision detection events. Here, only 10 and 6. So now we can talk about collision spaces. Let's imagine your final project that you're going to create a robot swarm, and it's a simple robot swarm. It's just 2 of these robots. You put 2 hexapod robots running around. You put all of the links of this robot in one collision space, and you put all of the links making up this second robot in a second collision space. At every point in time, among other things, your physics engine will detect whether the front right leg comes into contact with the front left leg, and it doesn't allow interpenetration. It says that shouldn't happen. It checks everything here, checks everything here, but perhaps as these 2 robots are walking around, they come very close to one another. As they come close to one another, these contact spaces, it's kind of like a box that the physics engine puts around these links and these links. These 2 boxes come into contact with one another. In this case, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 objects, 14 links. So we do this many collision detection events. Over here, we also have 14 links. We do the same number of collision detection events. What happens when the 2 collision spaces surrounding the 2 robots come into contact with one another? What does the physics engine have to do during that time step?
Is to now check collision between both of the robots.
Between every link in every robot for every robot against every other one. So hopefully you can see the intuition here. Collision spaces restrict the amount of computational effort that your physics engine has to do most of the time. If you start to create complicated virtual worlds that are composed of, for example, multiple robots, you can build in some intuition that there are certain links that are going to come into contact more often than other sets. And you can make things easier on the physics engine. Again, for our purposes, for most of this course, this is going to be irrelevant, but just to show you how complicated things get. And this is the reason why things get very complicated, get very computationally intensive in a physics engine. What we've just been talking about is known as collision detection. This is just knowing whether or not a collision is occurring. If, for example, the two front lower legs of our insect robot come into contact with one another, now your physics engine has to do some additional work, which is collision resolution. How does it resolve that collision? Here we've got two ball bearings that have come into contact with one another here. And my little visualization here is showing the hack that the physics engine uses to resolve this collision, which is the hack it always uses. It applies one force pushing this ball bearing this way and another force pushing this object this way. If they're ball bearings, they come into contact with one another. These forces will help these simulated ball bearings do what you think they should do, which is immediately head in opposite directions. Yeah?
This is not necessarily part of the same topic, but if you want to train a model or a robot to do something, and you only want an independent robot, but you want to kind of avoid having 50 worlds for every kind of iteration.
Not 50 worlds, 50 spaces or 50?
50 simulations going, so you have like 50 robots going at the same time, but
Oh,
you don't
oh.
want them interacting. Would it make more sense to have a world where they're able to like interpenetrate and not affect each other, or go have separate worlds?
Okay, great question, and this helps. So we're trying to build up an intuition today about physics engine, and this is kind of important to have this intuition because it guides how you go about creating complex simulations. So NASA hires you after you graduate from UVM, and you join a team about developing a swarm of 50 robots that NASA is going to send to Mars, and they want some help from you to simulate how these robots would do whatever they're supposed to do on Mars. And NASA says, oh, and by the way, they're all going to very distant places on the planet. So I'm going to answer your question with a question. Do we simulate all 50 robots in the same world? Or do we, and then put each one in its own collision space? Or do we create 50 different worlds and simulate them completely separately?
Say same world, because it's going to be more efficient than having to boot up multiple worlds.
Okay, so there's one possibility. So if you start up 50 instances on your laptop, maybe that's a bit of a headache because you've got 50 independent simulations running. However,
But you would also only have, or you would have fewer collisions that you would have to compute at each time. So maybe that is the trade-off, that you have more simulations, but you have fewer contacts that you have to detect.
great. So we've realized that there's a bit of a trade-off here, right? If we created one simulation, which typically requires just one process running on your laptop, that's good news. But now we got to create 50 spaces, and we're going to put the robots really distant from one another inside the virtual world. So these spaces are never going to come into contact with one another, we hope. Have we alleviated the burden on the physics engine? It turns out the physics engine still has to check whether these 50 spaces are colliding or not. It doesn't know. So there's a bit of an additional computational effort that would be required. So the answer to your question is, it's hard to know, actually. It depends on the details of the physics engine. But the fact that you know there's a trade-off, that's good news. You're using your developing intuition about physics engines. Yes?
I'm just curious, could you make one of the hitboxes for one or each robot, like as a whole, interpenetrable, so that it doesn't do the collision detection? So like robot 1, its links can't collide with itself, but that robot 1 can collide with robot 2.
Okay, another great. So let's make a wheel. Let's assume it's a wheeled rover. Yeah, it doesn't have any wheels. Wheels also are connected to the main chassis or the body of the robot with joints. Those wheels are never going to come into contact with one another. If they do, there's something seriously wrong with the rover. So we can turn off collision detection between all the objects within our simulated rover. The wheels still need to be detected whether they're colliding with the ground or the rover will sink through the ground. So yes, maybe we can get all of this back. And if we're dealing with wheeled rovers, or we can assume that the robot never self-penetrates, things get a lot easier and none of this really matters. All of this starts to matter when you have very complicated scenes in which it's hard to know a priori whether or not objects are going to penetrate one another. Okay, great discussion today. We'll pause there for today. You have a quiz due tonight. Some of you are working on assignment 3. Some of you are working on assignment 5 and 6. See you on Tuesday.